Good morning, everybody. So today we will finish chemical sensors, and then we will make some exercise. I have an example, and that's it. And we will finish this course. Yesterday we were talking about. Let me increase here the image. We were talking about sensors based on measurement of conductivity of electrolytes. Why? Because it's one of the ways that you can use to measure the concentration of a salt, for instance, in a liquid. And we saw that at least for small concentration, you can derive the concentration of the salt in the liquid by checking the electrical conductivity of that solution. Of course, this is pretty linear. That's nice. But as I've already mentioned, it turns out that the slope depends quite a lot on the type of salt that you have in the solution. So you must know what you are measuring. Okay. Now we have seen yesterday how to measure the conductivity simply by using the principle of measuring resistance. Okay. We have seen that you can do it with two parallel electrodes with some certain area. DC is not ideal because you might corrode the electrodes and you can create electrolysis. But so you would like to have it's better to use AC, but on the other hand, you must consider also the capacitances because as a matter of fact, you have an electrolytic capacitors, okay? So you must choose the frequency so that you minimize the effect of the polarization capacitance, of the impedance based on this capacitance, because the impedance, of course, depends on the frequency, and on the other hand, minimize also the effect of the geometrical capacitance and the cable capacitance, okay? Fine. Of course, you can also use these points electrodes where you can take only the voltage in the middle of the section and get rid of the non-linearities at the ends of the profile, which are given by polarization. Now there is another type of sensor based on measurement of conductivity. Again, we want to measure the conductivity of an electrolyte just to measure the amount of a salt, for instance, in this electrolyte, which changes the conductivity of the liquid. And it's based on the transformer principle, okay? If you want to measure the conductivity, you don't necessarily need to measure the resistance. You can use the system. And basically, this system is composed of two transformers, even if it doesn't look like from this sketch. Here in the drawing, you see that you have a pipe where you bring the liquid you want to measure the conductivity of. And then this pipe splits into a ring, and then it continues. It joins back on the other side, and it continues. So just imagine that the electrolyte arrives here, arrives to this ring, it splits, and it goes through this ring, and then it continues to the other way. Okay, so just imagine that you have, if you watch it from the top, like something like that, and then the electrolyte runs both ways. And it continues to the pipe on the other side. Fine. On the first side here of this ring, you have the first transformer. you have a core, a ferromagnetic core. You have a coil with N1 turns, and then you have a power supply which generates a voltage, UG in this case. The first part of the transformer is straightforward. You have a ferromagnetic core, and simply you create a magnetic flux. And where is the second part of the transformer? Transformer, you know, it has a ferromagnetic core, always. You have N1 turns here, and then N2 turns here, okay? And then the ratio is N1 over N2, okay? Here I see N1. Oh, sorry, mistake. My mistake. Let's erase. I apologize. So here you see a ring, okay? So precise. So you see the first N1 turns here, and you get the ferromagnetic core here with the magnetic flux as usual, okay? So the first part of the transformer is there, it's clear. You have ferromagnetic ring, you have this voltage, you have the magnetic flux, and where is the secondary coil? Well, the secondary coil is composed by one single turn of electrolyte. It has a conductivity, so some electric current can flow through this electrolyte. So just imagine that the electrolyte itself, this ring of electrolyte, is effectively as a one-turn coil, okay? So it's like if on your transformer, your typical transformer here, you have a one-turn coil, this one. So the ratio of the first transformer is a voltage transformer, which has a ratio N1 to 1. Here in the drawing, in the schematic, in the equivalent schematic, it's written N1 to N2, but N2 in this case is 1. So we can say that the ratio is N1 to 1, where 1 is the one-turn coil. So N2 is 1, okay? So here we have a transformer where we induce a ferromagnetic flux here in this core, which is equivalent to this ring, and then we create a current at the secondary coil, and the secondary coil, as a matter of fact, is just this ring of electrolyte. Now, what is the current which flows there? The current which flows there is given by it depends on the resistance of the electrolyte, okay? So you will have a current in this ring if everything else is constant. Of course, if we don't change the voltage at the entrance of the first transformer, you will not have anything changing, unless the current will be always the same unless you change the resistance of the electrolyte. which composes the one-turn coil at the secondary of this transformer. And basically, the current that you have here depends on the resistance of the electrolyte, and therefore it depends on the conductivity of the electrolyte, okay? Now, how can I measure this current? Well, I have a second transformer, in this case a current transformer, which has a ratio N2, that is 1, to N3, which has the purpose to amplify this current and give us a current which can be measured on an output resistor RZ, okay? So this is the first transformer. Let me emphasize it like this. Here, found. So let's say this is our first transformer, okay? Then you have another ferromagnetic core, where the primary now is the one-turn coil composed of the electrolyte, and then you have N free turns. So you convert the current here, I2, the electric current, I2, in this one-turn coil of the electrolyte. You convert this current into a current I3, and you measure it, for instance, having a resistor RZ here, and then measuring the voltage on the resistor, okay? As usually done, so you always like to have a current, not an open circuit, because you want to measure current, so you have always to short the output, and you measure then the voltage on this resistor, okay? So this is basically our second transformer, okay? So you have first a voltage transformer which converts the voltage and creates in the secondary, in this ring of electrolyte, a current, and then you convert the current in the electrolyte using this current transformer, which gives an output current I3, which is measured on as a voltage drop on RZ, okay? What is the advantage of this system? The advantage is that basically there is no contact with the liquid. In the previous examples, we have seen that we always have the electrodes inside the liquid, and we have seen that sometimes it's kind of nasty because it can generate chemical reactions you really don't want. In this case, on the contrary, the advantage is that you just have the electrolyte running in these tubes, in this ring, and you just use contactless method. So there is no electrode which touches this pipe. This pipe doesn't need to bring the liquid in contact with your electrodes. It's everything contactless, okay? So for instance, it's good for food industries because you really don't want to put some electrode in some material that eventually is food, so it goes in the mouth of your customers, okay? Now, we've seen yesterday, yes, I think we have already seen it, this measurement of oxygen, yes, based on the fact that the oxygen is paramagnetic, contrary to other gases which are common gases which are diamagnetic. And another system to measure oxygen is to use semiconductive sensors, which are based on the fact that here you see a schematic, and here you have some photographs. Basically, what you have is, most typically use tin oxide, SnO2, and you warm it up. So at the bottom, you have some heater. And what you do is basically to warm up this metal oxide and measure the resistance of this tin oxide depending on the oxygen. So here you have a schematic where you have some heating element here. Okay, so this is the heating element at the bottom. And then you have here schematically, you have, this is the symbol of the sensor itself. Then you have a resistance here, which depends on the presence of the oxygen, and you can convert it to voltage using this resistance to voltage converter. Okay. Now, why should the resistance depend on the presence of oxygen? Just imagine that the tin oxide is composed of grains, okay? So just imagine all these grains all together, and the current has to flow through these grains. Now, I know this image is not so clear, but if you watch carefully enough, and later I will upload the PDF to Teams, so maybe you can watch it better. Basically, what happens is that if you have oxygen, this will create a depletion layer in the grains of the tin oxide. Sorry. So that you see that the electrons here move at the center of the grain, and you have some potential barriers for the current to go through one grain to the other, to, let's say, jump from one grain to the other because of that. On the other hand, what happens if you have, for instance, oxygen, sorry, if you have, no, this is not oxygen, I said something wrong. This is not for oxygen, I apologize. This is to sense other gases which react with oxygen. Okay, it was good. So I have to correct this mistake in the slide. This is to measure the presence of gases which react with oxygen. So when these gases arrive, they, for instance, here you have the presence of carbon monoxide. The carbon monoxide reacts with oxygen, so it takes away, sort of saying, the oxygen. So the oxygen does not keep there at the tin oxide, and the potential barrier, so the electrons can be disposed around all the volume of the grain of the tin oxide, so the potential barrier gets lower and the current can flow more easily, and therefore it means that the resistance is lower. Okay. So again, I apologize for my mistake. This, well, theoretically you can, it does measure the presence of oxygen, okay? Because when the oxygen is there, it pushes the electron inside, you have depletion layer, and therefore the resistance increases. But as a matter of fact, these sensors are used not to measure the presence of oxygen itself, but to measure the presence of other gases which react with oxygen. So if the other gas gets there, takes the oxygen away, then there is it doesn't affect the tin oxide anymore, and the resistance can, the potential barriers decrease, and the resistance and the current can flow, so the resistance decreases. Okay. Another sensor for explosive gases is Pellistor, which is a thermocatalytic sensor, and is based on a simple platinum wire, which is warmed up, so you go around 300, even larger temperature. And inside you have some catalyst, which, again, I somehow simplify, but just to let you understand the principle. The purpose is to, of the catalyst, is to make possible to create a small burning of this combustible gas, okay? So you have some gas which, if reacts with oxygen, will release some energy. So there will be some micro combustion. And this energy will warm up the temperature of the platinum wire, and therefore you can eventually measure this increase of energy by measuring the temperature of the filament itself. Of course, in front of these sensors, there is always some protection, some sort of grid, very, very deep, which lets the gas enter, but it will avoid that the sensor will ignite some flames, okay? It's sort of flame barrier. I don't know actually what's the correct name, but it's a sort of barrier which avoids to create flames from the sensor to the volume where you have maybe some high concentration of flammable gas. So you don't want definitely to ignite your gas that you want to measure. So there is this very dense net at the top. Maybe you can see it here in this example I've put here. This is a typical industrial pellet store. So you can see here at the center the place where you have this grid. This industrial, so you see that you have this screw that you can, it's a standard dimension that you can screw on the place, on the volume where you have to measure the presence of these gases. Otherwise, like you can see even the sensor in the cheap meters, that this is a kind of old principle. It was very often used in these sensors that were used to detect the presence of gases around, like leakages and so on. And if you open them, there is this small sensor where you can see very well this protection against the flames. Okay, so basically you create some micro combustion of this molecule of these flammable gases inside the sensor. This will give some energy. It's exothermic, so it will release some energy, which will warm up the filament, and therefore you can measure the resistance. Okay, once you give a constant current, then you can measure the output voltage. In this case, for instance, you use a bridge because, as usual, you want to be sure that the change of temperature is given by the micro combustion of the flammable gases, and not by the fact that the temperature changes in the room by itself. Okay, so you want to be sure that the change of resistance is not given by a change of resistance in the environment where you are measuring, but it's an actual change of resistance given by the micro combustion of the gases. Why we have a catalyst? Because we want, of course, to measure also small quantities of gas, and therefore we promote the reaction of the gas by having a catalyst inside the sensor. Okay, so in order to have, maybe I forgot to finish the discussion here. In order to have this, so in order to make sure that you measure actually the resistance, the change of temperature given not by the change of temperature in the environment, but because of the micro catalyst, micro combustion of these gases, you have two sensors. One, it's in fact active, so it is exposed to this. You have two filaments. One is exposed to the catalyst, which makes the explosion. The other one, no. The other is identical, is fed by the same current, but will not feel the energy released by the reaction of these gases that you want to measure. So then you have them in the bridge, and as usual, in the bridge, you can, if you have a change of resistance of both filaments, the one which is exposed to gases and the other no, then it means that it's not a change of resistance given by the temperature change caused by the gases, because it happens on both of them, also to the one which is not exposed to the gases, and therefore being in two different sides of the bridge, they compensate each other, okay? So you don't see the change at the output of the bridge, okay? Fine. Another interesting sensor is the infrared gas detector, which is based on the fact that, as we have seen last week, if you take the energy in the wavelengths, in the infrared wavelengths, so if you remember, visible light is about from 380 nanometers to 780, something like that, 800 at most, I think, nanometers. And then above that, 1 micro and a larger wavelength, you have infrared, okay? And one of the problems that we have seen last week is that if you have, for instance, air, and you have wavelengths, you have energy, electromagnetic waves arriving in this infrared region, some molecule in the air will absorb that specific energy at that specific wavelength. Because of the structure of the specific molecule, then this will react with some wavelength, with some frequency, but not with other frequency. And that was a problem because we wanted the transmissivity of the medium to be 1. We want all the energy emitted by the body, we want to measure the temperature of, to arrive to us. Because we want to measure that energy to determine the temperature of that object, right? So, definitely, for us, having a transmissivity which was lower than 100%, it was bad. We wanted all the energy to come to us because we want that energy of that object to measure its temperature, right? Fine. So, in that case, I also specify that you can select, for instance, a specific wavelength where you know that you have transmissivity of 100% in order to focus the filter of your narrowband pyrometer and measure the frequency, measure the energy there, okay? That was a problem for infrared, for a contactless measurement of temperature, but in this case, it becomes a new opportunity. So the same physical principle, which was bad when you want to measure the temperature of an object with a contactless measurement, which is based on the fact that I want the energy emitted by the object, in this case is in fact an advantage because we can use this principle to measure the presence of those gases, which react with specific wavelengths, okay? So here, for instance, you can see a graph where I plotted the absorption rate for different gases. If you watch, for instance, CO2, carbon dioxide, at about 4.3 micrometers, you have an absorption rate which arrives almost to 90%, okay? And for carbon monoxide, this frequency, which is absorbed by the carbon, the wavelength absorbed by the carbon monoxide is about 4.6 micrometers. If you go to the lecture, to the PDF of the lecture we had last week, and you watch at the spectrum of the transmissivity, you find out it's exactly the opposite of this one. You will see that in that case we were plotting the transmissivity, which is the opposite of the absorption. So you saw that, for instance, at 4.3 micrometer, in the transmissivity, you have a huge decrease of the transmissivity because in that point, the CO2 is absorbing the energy. So it cannot be transmitted through the media. And here is vice versa. Here we are watching not the transmissivity, but its opposite, which is the absorption, And for instance, if you watch in that graph, you see that we have a transmissivity close to 1, or close to 100%, at about 4 micrometers, okay? So, how can we use this system to measure the presence of carbon dioxide or carbon monoxide, for instance? Well, we have a chamber where, where we inject some light, some infrared light, at a various, at wide spectrum of frequencies, okay? Then here we have a mirror. We will see later what we need it for. So the different frequencies enter in this chamber. They will react with the gas inside this chamber, and then they will be reflected back to our sensing area, where I have a split beam splitter. So the light arrives on this beam splitter, and one portion will go to one detector, and another portion will go to the second detector, okay? So, again, the infrared radiation goes there in the chamber. It will react with the gas. It will be reflected. And also when it's reflected on the way back, it reacts again with the gas in the chamber. And then once it arrives back, it's split in two halves. One half will go to one detector, and the other half will go in the second detector. Then what we do? On one detector, I have a filter which selects, for instance, 4 micrometers. So the first detector will check only the component at 4 micrometers wavelength of that light, which comes back after reacting with the gas inside the chamber. The second detector, for instance, will be focused, will be tuned, sort of saying, on 4.6 micrometers. So I watch only the portion of the spectrum around 4.6 micrometers. And then what happens? If you have carbon dioxide inside the chamber, this will be absorbed at 4.6 micrometers, you see? No, this is carbon monoxide, not carbon dioxide, sorry. I wrote here carbon dioxide, but it's carbon monoxide. Second mistake in the same slide, in the same PDF. So, the beam at 4 micrometers will pass through the gas without being absorbed, because it doesn't react with any of these gases that we have inside the chamber, okay? So the one at 4 micrometers doesn't care, it goes through, reflected, goes back, and bob's your uncle. It doesn't care about anything inside the chamber. But the beam, the light, the radiation, better, at 4.6 micrometers, then will be absorbed by the carbon monoxide, if the carbon monoxide is there, okay? So, if you watch here the response of these two detectors, you will find out that at the detector which measures the presence, the amount of radiation at 4.6 micrometers wavelength, you will notice that this will have a response which drops down if you have carbon monoxide inside the chamber, because that is telling us that the radiation doesn't arrive to the detector because it is absorbed by the carbon monoxide inside the chamber, okay? While we use two different sensors, we use two different detectors, one at 4.6 and one at 4 micrometer, isn't just enough to watch at 4.6 micrometer and observe when this amount of radiation decreases because it's absorbed by the carbon monoxide inside the chamber. As usual, we use always a comparison with another element, with another physical quantity, which is not affected by what we want to measure. Because as a matter of fact, this variation could be due I don't know. For instance, because the source of radiation is changing. So maybe it's not very stable, this source of radiation. Maybe it just drops for God knows why, what reason. So you have this light which decreases. You think it's due to the presence of the carbon monoxide inside the chamber, but in fact, no. The signal that you see at the detector at 4.6 micrometers did not decrease because you have a drop or because we have an increment of the carbon monoxide, but because we have, for instance, the source of light, the source of radiation, which decreased, okay? So, how can you avoid to have this misleading result from your detector? You have always another detector at 4 micrometers, which doesn't react with the carbon monoxide. It doesn't react with anything, because as you see here, the absorption at 4 micrometers is not affected by any other gases, so you don't have carbon monoxide, carbon dioxide, any other gases. So you select this point here where you have no problem with any other gases. And what you do is to check what you have at 4 micrometers. If you see that the radiation is decreasing also at the 4 micrometers, it cannot be the carbon monoxide. It's some other sources of error. For instance, the fact that the source of light decreased, okay? So you take always the comparison between these two wavelengths. One which is absorbed by the gas that you want to measure, and the other which in fact is not, okay? Now, pH meter. pH meter, they are used to measure the concentration of hydrogen ions in a solution. Probably if you worked in some chemical laboratory, definitely you have used some pH meter. How do they work? Basically, there is a probe, there's a glass electrode, which in this case, better. We have 2 electrodes. And even one is the electrode, the main electrode, which has a glass bulb here. This is a porous glass, especially designed glass, which absorbs the hydrogen ions on the outer part or at the inside and outside surface of the glass. And inside I have a solution which has potassium chloride at pH 7. So it's calibrated to have pH 7 inside. And you have an electrode of silver chloride inside this bulb, okay? And what happens? Basically, on the 2 faces of this glass substrate, glass bulb, you have an amount of hydrogen ions, which depends on the concentration of the 2 solutions. On the one side here inside of the bulb, and the opposite side outside or in the solution that you want to measure, okay? And the difference of charges of these ions, where, for instance, if you are measuring something acidic or basic, you have more or less ions in the solution compared to the standard neutral pH 7 that you have inside the bulb of this glass bulb. And therefore, if you have different amount of charges outside and inside, you have different charges, okay? So different potential, okay? So just imagine that you have this bulb here, okay? If you have H plus, H plus, H plus here, and you have outside more charges, then you have an electric potential, okay? If you have less charge, so here you have pH 7. If you have another concentration of hydrogen ions outside, you have another potential, okay? So, how do we measure this potential? Well, we need a reference electrode, which is an electrode with a porous membrane here. Again, you have silver chloride wire. And here we have saturated solution of potassium chloride, and it's used to have a constant a reference potential to the bath. Okay, so the reference electrode is there to have a reference point, because you want to measure voltage. You want always to measure the difference of potential. So you need to define a potential which is independent on what you're measuring, and that's a reference electrode which goes there. And then you measure the difference between that potential and the potential that you develop with this bulb there, okay? If you watch the difference of the potential, you find out that you have this characteristic. By the way, just a little remark. Very often nowadays you don't see two electrodes. You see only one, but as a matter of fact, they are. It seems that it means that they are together. Okay. So in the bulb here, typically you have, this is the first electrode, then you have here some ring, and then you have here the second electrode. Okay. So the second electrode, this is the first electrode, and this is the reference electrode. So even if your pH meter has only one device, one electrode, and you think it's only one, and you say, where is the reference electrode? The reference electrode is inside, it's always inside. So here you have the reference electrode, which is surrounding the main measuring electrode here, okay? So you have always the reference electrode, even if you don't see it. It's simply in a structure which surrounds the main electrode. And as I was saying, the voltage here depends on linearly on pH, and the slope is about 50-60 microvolts per unit of pH at around room temperature, but it kind of changes quite significantly if you warm up the solution. It arrives up to 74 microvolts per pH for a solution at 100 degrees, which is not something uncommon. When you have some chemical process, you definitely very often warm up the solution at such temperature. So, and the change of response is quite significant. Like we have roughly 50% more of voltage, if no, 50 more, something less. If you change the temperature about from room temperature to 100 degrees. So it's very important to keep in mind that the response of the voltage changes significantly with the temperature, which means that in most modern, if you have a good pH meter, digital pH meter, you have also a probe of temperature. So on the display, they show also the temperature, not only the pH, because then if the pH meter is smart enough, it's correcting automatically the value of the pH shown to you by reading the temperature and recalculating the response of the voltage for a given pH for that specific temperature. So it will know that for different temperature you have different slope of millivolts per unit of pH, and will correctly give you the result, recalculating, correcting the change of the slope for the temperature. Otherwise, you have to do it yourself. Back in the times when there were no digital pH meter, and you had some very analog system where there was nothing else than a voltmeter, where on a scale you had the millivolts and the other scale you had the pH. And then they said, well, this correspondence between millivolts and pH is valid for 25 degrees, for instance. And then you had always to measure by yourself the temperature and make your math and calculate the correction of the temperature, okay? Now, what is important for us electrical engineers is that when we get this voltage, we must be careful how to measure it. Why? Because in this case, we have a voltage which is created on a glass membrane, which has therefore a very large resistance, okay? And this is a problem. You know that when the voltage source has a large resistance, then you have to select a voltmeter which has an input resistance much larger than the resistance of the voltmeter of the source itself, okay? So just imagine that here you have your voltage given by the pH, and then a very large resistance, okay? Then you have your voltmeter here, and your voltmeter, of course, has some input resistance. We have always said, in theory, the voltmeter is an open circuit, but and for most of the applications, you can assume the voltmeter is an open circuit, but as a matter of fact, it's not. It has always some input resistance, okay? And in this case, it's not negligible, okay? So this is the resistance of the voltmeter. This is the resistance of the probe. And of course, here you will have a voltage that you measure, which is the voltage created by the probe minus the voltage drop on the probe of the resistance. And this voltage probe depends on the current that you have in this circuit. How to minimize the value here of the voltage drop that we lose on this resistance, simply limiting this current. So we have to keep this current as low as possible, which means that this must be much, much larger than the resistance of the probe, okay? Which can be in the orders of tens of mega ohms. So if this is tens of mega ohms, this should go in the orders of giga ohms, okay? Using mega ohms here for this voltmeter is not enough, okay? So you have to use giga ohms because this resistance is bloody high. Otherwise, you load your circuit, and then the voltage that you get here is not the same voltage of the probe, but you will miss a considerable amount of the voltage on this resistance of the probe, okay? So this is just to make it clear, this is your probe, okay? This is the voltage of the probe, and this is the internal resistance of the probe. So what you can do, for instance, as you probably can guess, is to use, before any amplification, you will use, for instance, a voltage follower, okay? Voltage follower with a specific op-amp, which reduces the current and therefore has an equivalent input resistance very, very large, okay? So let me erase this. If you remember, you use a voltage follower so that the voltage in the input is equal to the voltage in the output, and therefore, but here the current is 0, okay? So you don't have problems with this current. The fact that we have a very large current here, very large resistance of the probe, also tells you that you must be careful with the bias current, okay? Just imagine that you have an op-amp with a large bias current. Okay, oops, I moved this. Here we go. So let's say that you have this bias current here. And here you have a very large resistance of the probe. And here the voltage of the probe, okay? Now, what happens if you consider the effect of the bias current on the output? As usual, you should shut down other generators, and you consider only one generator at a time. So you shut down the voltage generator of the voltage of the probe. And you see that the current cannot enter in this ideal operation amplifier. It will flow here, and it will generate a voltage V prime, which is given by the resistance on the probe times this current. And this voltage, therefore, then will be by the voltage follower replicated, like brought out here at V out, okay? So if you have this resistance very large, you definitely need this current, this bias current to be very low to avoid finding here a very large voltage due to the effect of the bias current flowing through the resistance of the probe. Which means that you need some operation amplifier with very, very low bias current, okay? I don't know. If you watch pH meters nowadays, they also show results in terms of, like, for instance, 2 decimal digits of pH, okay? What does it mean? It means that here, let's say that you have a slope of 50, let's say about 50 millivolts per unit of pH. It means that here, this digit corresponds to 500 micro, okay? Now, if you want this to be not affected by, or you want this, is it correct? 1, 2, 3, 5 micro, 50 micro, sorry. Is that correct? Because this is 1 unit of here corresponds to 50 millivolts. Here, no, it's correct, 5 millivolts, and here 0.5 millivolts, okay? So 500 microvolts. Okay, so now, if you want a current, if you want a change due in the output due to the bias current, which is lower than 0.01 unit of pH, you have to choose a bias current that is in the order of the femtoamperes, okay? Just that you have here, just think that you have here, I don't know, 10 mega ohms. You have 10 to the minus 10 to the 7th divided by 510 to the 6th. So you just go in the order of the femtoamperes. And that is a problem because, you know, operation amplifier with femtoamperes bias current, it's something kind of expensive. Well, not dramatically expensive, but operation amplifier with tens of femtoamperes can go down, can be €1 or even, I don't know, some 2 years, something like that. Which is not dramatic, but you must keep in mind that if you, sometimes you see on internet they sell these pH meters, these very cheap pH meter, which show you 2 digits after the decimal point, and they cost like 10 euros, shipping included. Cannot be possible, because for that price you cannot afford some signal conditioning. Even I'm talking mass production, okay? So these prices of operational amplifier, I'm talking like for bulk numbers. For if you buy one of them, you can pay 3-4 years. But even if you produce at mass production, you cannot afford to have just the amplifier which costs 10% of the whole price. One operational amplifier which costs 10% of the whole price, including everything, shipping, the probe itself. It's not possible. So they will show you 2 decimal point, but if you make your math and you go down to check which is the bias current you need to see correctly this number, you find out that you need an operational amplifier with such a low bias current that you definitely cannot afford it for such cheap instruments. So this number is there, but it's pointless. It's not precise enough to have some meaning for this number. Okay. By the way, this probe always change quite often. So because they leak out some solution, and then you must be always careful how to treat it, not to. Because the membrane is porous to attract the hydrogen ion, so you must always keep it wet in some solution and all this sort of jazz. But calibration is always necessary every once in a while. So what you have to do is to put the sensor inside the solution with very well-known buffer, with very well-known pH. And typically you have to do it for 2 values, one larger and one lower than the value that you want to measure. For instance, if you want to measure pH around 7, you might use some buffer at 8 and 6, okay? So that you can measure the sensitivity in this area where around the value of the solution that you want to measure. And keep in mind also that, again, another important thing is that when you make your calibration, also the value of the buffer itself has some uncertainty. You make that calibration, and typically the pH of these buffers, of this solution that you use for calibration, is known within with 0.01 unit of pH uncertainty. So even there are some pH meters which have 3 digits, but they don't say much if you make the calibration with some buffers which have uncertainty at the 2nd digit. So the 3rd digit is there, but it's below the uncertainty that you use for calibration. Okay. Now quickly, because I still have half an hour, and but I can maybe continue later longer. If there is nobody else coming later, I can continue the exercise, taking my time. Our ion-sensitive field effect transistor. It's a field effect transistor, as usual, but in this case, we create the channel for the electrons to go from source to drain. So this structure may be overcomplicated. Just think about this. You have the source, your drain with the contacts, and you want, of course, to create a channel for the current to go from source to drain. Okay, so you need some electrons here in this area to have a channel for the flow of electron, and therefore having the current. And how do you do it? In this case, you have an electrolyte here, and you have an ion selective film which attracts for instance, in this case, ions of hydrogen, positive ions of hydrogen. They are attracted there, and these positive ions of hydrogen will take up from the substrate the electrons, creating this channel which can flow then. Okay, so here the point is being able to create a film which is able to attract from the electrolyte these positive ions of hydrogen to create the gate, the effect of the gate, so instead of creating this effect using some electric field, you use this, well, at the end of the day, we still use the electric field, but we control this by using a film which attracts ions of hydrogen if you want to measure the concentration of ions of hydrogen, and this is used as an alternative method to measure the pH. So there are pH meters which are not based on this glass bulb with the porous membrane which attracts the hydrogen ions, but it's based on this field effect transistor where you have a selective film which attracts the hydrogen atoms, the hydrogen ions, and therefore create the gate, okay? Capacitive sensor of humidity, very common sensors. They are basically a capacitance which change the dielectric constant according to the humidity. We have seen many sensors where we studied the capacitance changing for the dimension. For instance, if you change the distance between the two electrodes. In this case, we don't change the geometrical parameters, but we change the material between the electrode, and specifically we change the dielectric constant of this material. How do we do it? We have an hygroscopic polymer which absorbs the water in the air. The humidity basically is the relative humidity is the amount of water that you have in the air. Okay, so when you say that the humidity is 50%, what do we mean? It means that for that specific temperature, you can inject in the air, you can vaporize in the air a certain amount of water. For instance, in this room, we have 20 degrees, and I know that I can, here, if I put a pan with some boiling water, I can create some vapor which fills this room with some air, some vaporized air, until a certain point. If I try to increase the humidity, then it will condensate simply because the air cannot take it anymore. I cannot inject more vapor in the air because it cannot stand it. So somewhere it will condensate and it will create some drop, okay? That is 100% of the humidity. If you say that you have 50% humidity, it means that in the air, there is some water vaporized, which is 50% of the most of the maximum that this volume of air can take at that specific temperature. So this sensor will absorb the humidity from the environment. It will change the dielectric constant of this capacitor because water has a dielectric constant which is about 80, when the typical polymer itself has a dielectric constant which is about from 2 to 10, okay? So if in the same volume you have some molecule of water, then the dielectric constant of the whole material will significantly increase, okay? And then we have studied how to measure the capacitance, you remember it, but a very common system in this case to measure a change of capacitance is to put this sensor in resonance with an inductor and then measure the change of the resonance frequency, which is given by the fact that you change the capacitance, and then you measure the frequency, which is very simple because you just need to measure difference of pulses. You just need to count pulses. Measurement of dew point. Dew point is you know what is dew point? Basically, if you have a certain amount of humidity in the air at a certain temperature, well, then the air can take less or more water before condensing, depending on temperature, okay? So let's say that now we have, I don't know, 60% humidity here, and this with 20 degrees. And the water and the environment is able to take this humidity. But if I decrease the temperature, I arrive to a point where the air cannot take this whole amount of water in the air anymore, and it will condensate, creating dew point, okay? Creating the dew. And that is called dew point. Dew point is the temperature where you create dew because the water, the air cannot stand, cannot take all this amount of vapor anymore. Okay? That's what you see in the morning if you go out early enough and it's very cold. You see that it's very cold, so at such a low temperature, the air cannot take much, cannot keep so much vapor in the air, so it does create dew. And how do you measure this dew point? Well, you can measure temperature, you can measure the humidity, and you make some calculation. But there is this very interesting method, which is a direct measure of the dew point by creating dew. So what you do here is to have a mirror which is cooled down, for instance, by a Peltier cooler, which is very simple because you just need some current. And it's not efficient, of course. Peltier cells are probably the worst in efficiency when it comes to thermal efficiency, but it's very simple. You have there your Peltier cell, send some current, you don't care about energy now, and you cool down this mirror, okay? And then what happens? You have a source of light here, which is reflected by this mirror and received by a photodetector. Okay, so you have your mirror here, you have a source of light, it's reflected by this mirror, and is received by a photodetector. And if there is no dew, the mirror is reflecting perfectly, and Bob's your uncle, no problem. But when you cool down to the temperature, you cool down the mirror to the temperature where you create dew, then the mirror will be covered by the dew, so it will not be reflected anymore, and the detector will not feel the light, will not receive the light anymore, because the mirror, in fact, is not a mirror anymore. It's covered by the fact that you created dew by cooling down at the temperature, which is exactly the dew point. And when you see that the light is not reflected anymore by the mirror, you know that you cool down to the dew point, and that is the temperature of the dew point corresponding for that humidity. So you directly measure the temperature where you achieve the dew by creating the dew itself. Okay, there's nothing like nothing more direct than taking this measurement, directly creating the dew. Of course, as usual, you want to have a reference for given humidity to avoid these gases. So here you have the same type of system where you have a light emitter and a detector, but there is no mirror, it's direct, so you always take the light, so it's not affected by the presence of the dew on the mirror, okay? And of course you get differential response, as we have done multiple times in this course. Just a minor remark. Be careful about this mirror. Don't use a glass mirror, because the problem here is that you need some isothermal block where the temperature that you measure, for instance with any sensor of temperature, is the same temperature of the mirror where you get the dew. And the glass mirror with some Peltier cooler under that can have substantial temperature gradient. So what you measure with the sensor of temperature is not the same temperature that you have on the mirror. So in this case, from the practical point of view, it's much better to get a block of copper, for instance, okay? And you polish it very, very, very well. So you create a mirror by polishing the copper, very, very smooth, so that it becomes reflective. And then you measure the temperature on this block of copper, which is big enough to be isothermal, and the temperature of the mirror is the temperature of the block of copper itself, okay? Fine. Now, it's over for this lecture. I still have 50 minutes, so I'm not sure I will be able to make this this example, so I will try anyway, and then, but if nobody comes here to kick me out, I will just make the example, okay? And we can see some numerical example. By the way, it's at this point you should be able to solve this problem by yourself, because we have already seen a couple of examples of uncertainty. And once you understand how to calculate the uncertainty of derived measurement ones, basically you have understood it for all. But I prepared some example. I'm not sure if I sent you this PDF before. I checked, it's not one of those that I've already solved in class. So I should be fine. Because, you know, at my age, I start forgetting what you've done and what not. So I watched the videos to see if it was one of the exercises we have already done. And it seems we are all fine. Okay, so very simple problem. You want to measure a small resistance, Rx, and you want to use the comparison method. Let me increase a bit. How do I? Okay. So that you maybe can read it. And you want to use a comparison method. Why? I've seen during the lecture that, for instance, if you have a very small resistance, if you want to measure a significant voltage, to measure that resistance, you need a large current. And measuring large current is not something easy. So it's much better to use a series resistor of known value as a resistive standard. In this case, we want to measure something around 0.1 ohms. So also the standard is in the same order of magnitude, 0.1 ohm. And measure the voltage drop on both the resistance that we want to measure, Rx, and the resistance on the standard, and then compare. They will have the same current because they are in series. So the resistance that we want to measure is proportional to the voltage on that resistor, Rx, Vx, divided by the voltage on the standard times the standard. Okay, they have the same current, so the output resistance will be the resistor of the standard times the ratio of the voltage on the standard itself on the unknown resistor divided by the voltage on the standard. So if, for instance, the resistance here is half of the standard, here the voltage will be half of the voltage on the standard, and vice versa. If the resistance that you want to measure, Rx, is twice the standard, you will get on that resistor twice of the voltage, okay? Now, the advantage is that you don't have to measure the current. So why we use this method is that you don't care about the current. If you don't know the current, it's just fine. You don't need to know it precisely. So you get rid of the problem of measuring a large current. The resistor standard that we are going to use is this 2792A03 of the Yokogawa, which is a Japanese company making some very nice toys, which has 0.1 nominal resistance and 50 ppm accuracy. Okay, so it's this one. It has 0.1 ohm nominal value. The accuracy is 50 ppm. Okay, so the resistance standard is 0.1 ohm, and it has an accuracy which is 50 ppm. ppm means part per million, okay? ppm stands for parts per million. It's so small that instead of giving the value in percent, they give you the accuracy in part per millions, okay? Then we have a temperature coefficient, which is plus minus 5 ppm per degrees. And, well, very important, the drift per year. So this is when you bite, but then if you wait long enough, it will drift. So, and quite significantly, the amount of drift per year is the same amount of the accuracy. Okay, so if you wait 10 years, then your accuracy becomes 10 times worse. And then you have a maximum current of 5 point something amperes. Okay, 5 point. It's basically they have 3 volts. These standards have all 3 volts. So according to the resistance, you can get more or less current. In this case, for 3 volts and 0.1 ampere, we get 5.5 amperes maximum current. Okay, always check that the power that you are using for your resistor is lower than the maximum allowable current. Okay. Then both voltages have a voltage. Both voltages, sorry, are measured using 2 HP voltmeters. Okay. And these are the accuracy specifications of the HP 34401A multimeter. And you measure V1 0.50032 volts and Vx it's 0.514074 volts. Okay. We have to calculate the value of the unknown resistance and its uncertainty, both using this method and both using direct measurement of resistance. Okay. Here you can see that you can measure a resistance of 0.1 ohms using this multimeter. And you need only one. You don't need 2 multimeters, and you don't need the standard. So why the hell should I complicate my life in using 2 multimeters and the resistive standard, which is kind of pricey? Like I was checking before. If you can go on eBay and find some used ones. So new ones go to all the way to $2,500. Okay. You can go down to about $2,000, something like that, buying some used one. As you see here, this is, for instance, calibrated in 2019, July 13. Okay. So of course, when you buy these devices, you must always check the calibration date because, as you saw, it drifts with time. If you buy something which is calibrated 5 years ago, then the accuracy they tell you, is not valid anymore because you have also the drifting time. So you must consider the price of having an extra calibration, which is not trivial. Okay. So why should I use this? This system with 2 multimeters and a very expensive standard when I can use directly the resistance mode of this multimeter. I connect I use 4 wires method, as you know, to reduce the effect of the resistance of the cable, and I can use directly this measurement of resistance of the multimeter. So why should it complicate my life? Well, today we make some calculation and we find out what happens if you use one method or the other. Okay, so let's start with calculating the value of the resistance. Okay, so the value of the resistance, as I said, is given by the resistance, by the voltage on the resistance that we want to measure, Vx, divided by V1 times the resistive standard. So it will be 0.514074 0.074 divided by 0.50032 times 0.1 ohms will give you 0.102808 ohms. Now, typical mistakes that I've seen in exams is to see multiple, too many digits after the decimal point. Why? Because the calculator is giving you this digit, and you say, why not writing them down? But be careful, if I'm using a multimeter with 6, in this case 6.5, significant digits, the result cannot have more than 6 digits, okay? If you have the measurement done with 6 digits, also the result must have at most 6 digits, not more, because those numbers are given by the calculator, are not given by the measurement instrument, okay? Fine, what about the accuracy, the uncertainty? Here we have 3 sources of uncertainty, okay? In this circuit, we have the uncertainty of the 2 voltmeters and the uncertainty of the resistive standard. Okay, so let's calculate very quickly the uncertainty of the first voltmeter. So the accuracy of V1. If you watch in the schematic, in the accuracy here specifications, we are measuring in the 1 volt range, okay? So we are measuring half a volt. It means that we are measuring in the 1 volt range. It was calibrated 6 months ago, so we are within 1 year of the calibration. So we have an accuracy which is 0.04% of the reading, which is V1, plus 0.0007 times the range, which is 1 volt, and this gives you an output of, let's write it down here because it's important, 20 microvolts, roughly, plus 7 microvolts. So you have about 27 microvolts, okay? And when you calculate the uncertainty of V1, you get the accuracy of V1 divided by the square root of 3 because we assume uniform distribution, and we get about 15.6 microvolts, okay? Fine. The uncertainty of the chalks. The accuracy of Vx is very similar because we are using the same type of voltmeter, and the amount of the value of the range is the same. The value of the voltage is almost the same. So when you make your calculation, you get that the uncertainty of Vx is 15.9 microvolts, okay? Because here you have V1, which is, no, this was for Vx or V1. V1, yeah, this was for V1. For Vx is slightly bigger, correct? So Vx is slightly bigger, and therefore you have larger component here. Vx is slightly bigger, so you have 20.6 microvolts instead of 20 microvolts, and you get slightly bigger uncertainty here. What about R? So what about the uncertainty of R? So the accuracy of R, we said, is 50 parts per million, okay? Times the resistance of the standard, which is 0.1 ohms, and therefore we get about 5 micro ohms, okay? 5 times to the minus 6 ohms. And if you calculate the uncertainty of the resistance, you get the accuracy of the resistance divided by square root of 3. Again, you assume uniform distribution, and it's about 2.89 micro ohms, okay? Fine. Then you have these 3 sources of uncertainty: the uncertainty of the voltmeter V1, the uncertainty of the voltmeter Vx, the uncertainty of the resistance, and you know how to calculate the derived uncertainty, okay? So let me erase, okay, let me write these values here. So the uncertainty of V1 is 27 microwatts, okay? The uncertainty of V2, Vx is, no, sorry, it's not 27. It's 15.6 microwatts. The uncertainty of Vx is 15.9 microwatts, and the uncertainty of the resistance is 2.89 micro ohms, okay? Okay, the time is over, but let me check if somebody is waiting outside. No, there is nobody, so I can continue, and hopefully nobody will kick me out of the room. Fine. So, meanwhile, I became a master of cleaning the boards. How to combine these 3 values of uncertainty to find out the uncertainty of the resistance? Well, we have to calculate the derivative of the resistance Rx, not this one, sorry. You have to find out the uncertainty of resistance Rx, okay? So now we want to calculate the uncertainty of the resistance Rx. So we take the derivative of Rx with, to the respect of Vx, and is R divided by V1, because the equation that you have to consider is Rx equal to Vx divided by V1 times R. So this is the equation. So if you take the derivative of Rx with respect to the respect of Vx, you get R divided by V1. And if you plug the numbers, you get about 0.199987, and you have the unit of ohms divided by volts. Then you calculate the uncertainty of the resistance Rx to the respect of the resistive standard R, which is Vx divided by V1, and it's about 1.02882. Okay, maybe the last digits you could forget it because you have already 1, 2, 3, 4, 5, 6 digits here. And this is unitless because you have volts over volts. And then you have the derivative of Rx to the respect of V1, and it's negative Vx times R divided by V1 squared, and you get negative 0.20563, and the unit here is ohms divided by volts, okay? Then you calculate the uncertainty of the resistance and the unknown resistance Rx as the square root of this derivative to the respect of Vx times the uncertainty of Vx. So you have the derivative of Rx with the respect of Vx times the uncertainty of Vx squared plus the second contribution is given by R, fine. You have the derivative of Rx divided by, to the respect of R and times the uncertainty of R, again squared, plus you have the derivative of Rx with the respect of V1 times the uncertainty of V1. We have already done it multiple times, so you know that the derivatives tell you how much this uncertainty will affect the final measurement, the uncertainty of the final measurement, okay? So if you plug your number, and I hope I didn't make any mistake because I made this calculation this morning at 6:30 during my breakfast, you find out that you have 3.17 10 to the minus 6 squared. Then you have plus negative, but you don't care because you square it. 2.97 10 to the minus 6 squared plus 3.2 10 to the minus 6 squared, which eventually give you 5.39 micro-ohms, okay? So you have free contribution all around 3 micro-ohms, and if you sum them quadratically, you don't get 9 micro-ohms, but because you sum them quadratically, they don't increase that much, and you get only 5.4 micro-ohms, okay? So this is the uncertainty that you get using this method. It's true, you have multiple sources of uncertainty, because you have the uncertainty of the first voltmeter, the uncertainty of the second voltmeter, and the uncertainty of the standard resistor, okay? But you get this 3.4 about micro-ohms, okay? What happens now if you calculate, if you measure this resistance with the direct ohmmeter that you have here on the multimeter, and instead of using this comparison method, okay? So use this ohmmeter, and you have the range, which is 100 ohms. The smallest range of this ohmmeter is 100 ohms. And we have accuracy specifications also for this mode of the multimeter, okay? Very painful for ears. Now, here we see that for calibration within 1 year, we have the range of 100 ohms, and the, let me see, calculation, the accuracy of this direct measurement of resistance is given by 0.01% of the resistance plus 0.004% of the range, okay? Let me check, because again I did it this morning. 0.01% of the resistance times 0.004% of the range, which means that you have 0.01% of about 0.1 ohms, 0.1, let me see, this resistance was 0.02, something like that, but this is not important, and you will see very quickly why. Plus 0.004% of the range, and the range here, you see we are using this range, is 100 ohms. So here you have 100 ohms, which means that this is negligible, basically, and the main component will be this one. It will be 4.01 milliohms, okay? So you get 100, and you get 4 milliohms, which means that the uncertainty, again, if you assume uniform distribution, will be the accuracy of the resistance divided by the square root of 3, and if you have about 4 milliohms divided by the square root of 3, you get about 2.3 milliohms, okay? And now let's compare the uncertainty that we have measuring the straight measurement of the resistance on the resistance mode of the multimeter with the uncertainty we achieved before using the comparison method. So here, if we connect directly to the multimeter, we achieve 2.3 milliohms of uncertainty. Here, we have an uncertainty which is 3 orders of magnitude smaller. So definitely it's better to use a comparison method, even if it's more complicated, even if you have to use 2 multimeters and an expensive resistive standard, because the uncertainty that we achieve is much smaller. But this shouldn't surprise you. Why is the uncertainty here much larger? Because we are using a range of 100 ohms to measure. So our range here is 100 ohms, okay? This is our range. And we are using it to measure a resistance which is 0.00100. So we are using it to measure resistance which is much smaller than the range. And in the accuracy, you see that there is a component which doesn't depend on the measured value, but it depends on the range. So you always have this component proportional to the range, regardless the value that you measure. This component, which is quite large, and we will see it in a moment, will weight more if you are measuring something very small, because it's always the same. But if you are measuring something small, it will be larger compared to what you are measuring, okay? That's why you always want to measure at a scale which is as low as possible, to have your measured value as big as possible compared to the range. So definitely this amount has a very large weight compared to the resistance that we are measuring, because it's very small, and this is always the same because it's proportional to the range. Doesn't depend on what you are measuring. And you will see here that, in fact, this value of proportional to the range is bigger when you have small ranges, okay? So not only you want to measure a quantity which fills the range, sort of saying, but you also want to have a quantity which is, you also want the range to be large, because when the range is not too large, of course, but because then you have other problems, but when the range is too small, then you have all these sort of problems we have studied in this course, which make the accuracy to get worse just because you have a small range. So everything gets complicated as small values of measured range, okay? And you see here what's happening. Here you have basically only 1 milliampere with this method, which means that you have the same resistance, but 1 milliamp means that the voltage is about 100 microvolts. Think about that. So you have 1 milliamp over a resistance which is about 0.1 ohms. It means that you have about 100 micro, okay, correct? Yes. So you're measuring a voltage which is 100 microvolts. Here, when you use this method, you use a voltage which was like 1 to 3 order of magnitudes bigger, because you have 0.1 ohms, so now you have times 5 volts. By the way, I didn't show that here. If you have this voltage, it means that you have of 0.5 volts, it means that the current is about 5 amperes. And if you watch here, we are all fine with this current because this standard can stand 5 amperes. So we are not destroying our system. We are we are using only a maximum current of 5 amperes, which is allowable by this standard, okay? So instead of using 1 milliamp here, as in the direct measurement of resistance, we're using 5 amperes, which means that we have a current on the same resistance, which is 3 orders of magnitude bigger, which means that the voltage will be 3 orders of magnitude bigger. So instead of 100 micro, you get 0.5 volts, okay? And therefore, it's way easier to measure 0.5 volts than 0.1, than 100 micro volts. And that's why you get lower uncertainty. So this example was just to show you that, yes, you might have this instrument in your laboratory. You see that it measures the resistance that, that you want to measure. But if you connect simply the ohmmeter, it will give you some uncertainty, which is not negligible. Here you have 2 milliohms over 100 milliohms, so it's about 2%, the uncertainty. Here you have an uncertainty much lower, 3 orders of magnitude lower, simply because you remember that you can use 2 of these multimeters and use a larger current, about 5 amperes. You don't have to measure the current, so you don't care about measuring the current, which could be complicated. For instance, here, at most, you arrive to 3 amperes, so you cannot measure directly 5 amperes, okay? And the uncertainty is much lower because even if you have 3 contributions, these 2 contributions are quite small, and of course you must use a standard which has small uncertainty. So the accuracy of this standard should be good. Here I intentionally chose a standard, very expensive standard with 50 ppm, but and these 3 contributions are more or less the same. If you increase the standard by 1 order of magnitude and it gets 1 order of magnitude bigger, still you have 2 orders of magnitude lower uncertainty. Okay, so even if the standard is not so good, you still have some advantage. So remember that there are several methods to measure a physical quantity, in this case resistance, and the method that you use will affect the result. So it's not just the instrument itself, but the way that you use it, like in this case, instead of using the same instrument as an ohmmeter, I use it as a voltmeter. Eventually, if you don't have 2 of them, you can first measure 1 voltage and then the other. It's not ideal, but we can approximate it. And that just with the standard, you can have a better measurement. So always remember that you must think to what you're doing. It's not sufficient just to take the best instrument ever, but always how to use it for that specific measurement will give you a totally different result in terms of uncertainty. Then here, just to finish, because I still have to check out if somebody's here. Yes, tak chvilku. Yeah. Then there is an example here to calculate the change of resistance. If you have a standard which changes the temperature by 2 degrees from a room temperature of 23 degrees. Why? Because this have a temperature coefficient about plus minus 5 ppm. It's not linear, so here you have also the second, like I can show you here. These are, this is the error in ppm given for different standards that they sell. And you see here, this 5 ppm per degree is given around the room temperature, okay? So, and it's not linear, so it could be slightly positive, slightly negative. So that's why you have plus minus ppm. But let's assume that you have the worst case, so let's assume 5 ppm. And for 5 ppm per degree, if you have, let me erase here. So for instance, a change of, let's say, we said, beep. So if the temperature changes by 2 degrees, then the difference of resistance will be 5 ppm times the resistance itself. So, sorry, it's about 0.1 ohms times 2. So this is part per million per degrees times 2 degrees. So you get about 1 microohms. And this means that the resistance that you measure, the resistance of the standard, will be, so the resistance at 25 degrees, because we move from a room temperature of 23 degrees to 25 degrees, 2 extra degrees, will be 0.10001 ohms, and therefore the resistance that you measure will be Vx divided by V1 times now R prime, not R anymore, so we increased the resistance of the standard, we increase also the resistance that we measure, and it will be 0.10289, okay? So, roughly speaking, if you change 1 micro here, you change also 1 micro here, basically. That's basically the same. And be careful, now we change the temperature by only 2 degrees, which is something can easily change in the environment, and you get 1 micro, which is not that smaller than the uncertainty. So be careful on not having large changes of resistances, because then you go to values of resistance that can be comparable with your uncertainty, okay? Otherwise, you have a very nice standard, but then the effect of the temperature is larger than the uncertainty itself of the standard. Okay, that is everything for today. Sorry if I took, I took 25 minutes more than necessary, but at least I concluded these exercises. And this was everything for me. I hope you enjoyed this course. I obviously apologized for all the mistakes I made in speaking. Of course, I'm not a native speaker, so clearly my English sometimes fails, especially because we are in this kind of environment where I don't have people in front of me. I have an empty classroom, and sometimes I get a little bit nervous in talking because I know that everything is recorded, and I'm overstressed about talking because I know I make mistakes and they will be there on YouTube forever. So again, I apologize for my mistakes in speaking English. I apologize for my typos, my everything, my mistakes I did also today in the PDF. I apologize if sometimes the lectures were not as good as usual because, again, it's not easy to talk to the walls for 2 hours. Nevertheless, I hope that you enjoyed this course, and I hope that you learned something that you might use for the next steps of your career and for your professional life. And for me, now we have again one lecture when we make only question and answers, and for me, it's everything. Thank you very much, and as usual, stay safe.